Welcome to the deep dive. Today we're looking at something, well, pretty out there. A theory asking a question that feels almost like science fiction. What if the biggest problems in physics aren't fundamental mysteries?
What if they're just bugs?
Exactly. Bugs in the universe's code. We're diving into QuQ, that's quantum unifying cosmology.
Right.
And the core idea from its creator, who goes by Count Kelvin Zero, is pretty wild. It says the universe isn't this, smooth fabric of space-time we always hear about.
Nope. It's more like a dynamically rendered quantum GPU.
Yeah.
And sometimes it lags.
A laggy GPU. I love that. But there's a serious side too, right? Count Zero calls it QuQ, which apparently is the sound you make during an existential crisis.
Yeah, there's definitely a layer of, let's say, cosmic trolling involved. It's playful. But underneath, it's presented as a serious, potentially peer-review-ready framework. And it claims, quite boldly, to make more sense of things than the standard model does for certain big issues.
All right, so that's our mission today. Cut through the trolling, the playful stuff, and really unpack the substance here. We're moving away from the idea of the universe as this perfect, unchanging thing.
But a smooth piece of cloth.
Right, and instead exploring QuQ's idea reality as this constantly updating information processing system, a system that's maybe not perfectly optimized.
And if that's true, if reality is constantly resolving itself, maybe subject to, computational limits,
then those big headaches like dark energy or the Hubble tension might not be deep cosmic secrets after all.
They could just be side effects. Artifacts of, badly optimized code running the show. Our current reality status, maybe? Loading. Quantum mesh unloaded.
Okay. Let's dig into that computational premise then. QuQ starts with this really foundational claim. Reality isn't solid. It's not fixed.
Right. It's actively computed. Like a sequence unfolding moment by moment.
And what's driving it?
Mathematical logic. And crucially, computational efficiency. The system wants to run smoothly, effectively.
So this flips how we usually think about math, doesn't it? We tend to see math as the language we use to describe the universe.
Exactly. But QuQ says, no, mathematics is the base code. It's the executable.
And physics, all the laws, the particles, everything.
That's just the compiled math.
Yeah.
It's running in real time. The chair you're sitting on, it feels solid, stable.
Yeah.
But according to QuQ, that's just an emergent property. It's the result of this continuous underlying information process churning away.
Which brings us to the engine room. Count Zero has a name for this, right? The real engine.
That's the one. Relativistic, emergent, adaptive logic engine. Quite a mouthful.
It is. What is it supposed to be?
It's pictured as this adaptive rendering system. Essentially, a self-optimizing quantum computer running the whole show.
Okay, an adaptive quantum computer. The source uses a software analogy I liked.
Yes. The Windows 95 comparison.
Right. If modern physics, with its separate bits for relativity and quantum mechanics that don't quite mesh, if that's like Windows 95.
Then QuQ positions itself as the Linux kernel of the cosmos. Flexible, adaptive, built for self-optimization. Much more integrated.
Okay, Linux kernel. If it's adaptive, self-optimizing. What does that mean for the things we think of as fundamental constants? Speed of light, Planck's constant. Are they not constant?
That's a huge implication. QuQ suggests they aren't bedrock laws carved in stone. They're more like optimization parameters.
Parameters, like settings the system has settled on because they work best for efficiency.
Precisely. Dynamically maintained settings, not immutable truths. And thinking this way completely reframes space and time, too.
How so?
Well, old physics tends to view space-time as this continuous geometric sheet, right? QuQ says forget that. Think of it as editable source code.
Editable source code. So moving from point A to point B?
You wouldn't necessarily have to travel through the space in between. Theoretically, if you could access the code, you could just rewrite your position.
Rewrite your coordinates. That's a massive conceptual jump.
It is. But it leads us neatly into how QuQ tackles quantum mechanics. All the weirdness.
Yeah, the uncertainty, superposition, entanglement.
Yeah.
Why does quantum mechanics seem so strange?
QuQ argues it only looks weird because we're catching the calculation in progress. We're seeing the system before it's finished rendering the outcome.
So it's not actually weird, it's just pre-rendering.
Exactly. Before the system commits to a final state, it's calculating various possibilities, various probability expressions. It's like preloading different potential outcomes.
Okay, so then the famous wave function collapse, that moment when observing seems to fix reality.
It's not some deep philosophical mystery in this view. It's just the system finalizing the frame, locking the event into the database, so to speak. making it definite because it needs to be rendered for an observer.
So Schrodinger's cat, the classic thought experiment.
It isn't magically alive and dead. It's the system holding multiple potential outcomes in the calculation buffer until an observation forces it to resolve, to commit to one definite state, alive or dead.
But wait, if there are potentially infinite possibilities being calculated, wouldn't that just overload the system? Wouldn't the universe crash?
That's a critical point.
Yeah.
It absolutely would. And that's where something called the plausibility filter comes in.
The plausibility filter, what's that?
It's like a set of constraints built into the real engine. It ensures logical consistency, structural stability. It stops things from getting too weird.
Like guardrails.
Sort of. Think about a video game engine. It has rules, right? Physics rules that stop you walking through walls, usually, or flying off into space without a reason.
Unless you find a glitch or a cheat code.
Exactly. The plausibility filter enforces the basic rules of the reality simulation.
So, the everyday physics, we experience gravity making things fall, objects staying put unless pushed. That's not the deepest layer of reality.
According to QuQ, it's more like a fail-safe mode, a high-level set of rules designed to keep the simulation stable and computationally manageable for the most part.
And this filter, it also relates to things like time travel.
It does. The source material suggests time travel isn't strictly forbidden by the underlying code. But it's incredibly computationally expensive.
Right.
Think about the amount of historical data you'd have to rewrite, the causal chains you'd disrupt.
It would break the simulation's consistency.
Right. So the plausibility filter generally blocks it. It requires an enormous, overwhelming input force, or maybe some kind of exploit to even attempt it.
Okay, this is where my mind starts to bend a little. The idea that reality isn't just computed, but it's adaptive, based on us, on observation.
The multiplayer instance idea, yeah. The world we experience isn't necessarily a single fixed thing. It's more like a shared instance that updates based on collective observation.
So the observer effect in quantum physics gets a different spin here. It's not that my looking collapses the wave function.
It's that the system has to allocate resources to render a finalized state for an active observer. It needs to make things definite when someone's looking.
So if the tree falls in the forest and literally no one is there to observe it,
reality might just be buffering. It's holding off on the final render, waiting for an observer interaction to force an update and lock in whether the tree is definitely fallen in the database.
I have to admit that feels a bit shaky. Doesn't that make reality fundamentally unstable? Or worse, dependent on me looking at it, solipsistic almost?
Yeah, that's a fair question. And QuQ tries to address it by emphasizing that the system prioritizes stability. It's not about every single individual continuously observing everything.
So it's more about sufficient collective awareness, a sort of consensus reality.
Something like that. Enough observers interacting with a part of the simulation forces it to maintain consistency there, and consciousness plays a key role.
How so?
In this model, consciousness isn't just some random biological emergent property. It's treated more like a localized process.
A processor, like my brain is part of the real engine.
Not quite part of it, but interfacing with it. Human consciousness is framed as an API, an application programming interface.
An API, so we can interact with the code.
In a limited way. Think about thought, intention, maybe even prayer. QuQ presents these as potentially being like API requests.
Requests sent where?
To the underlying probability layer of reality. You're not rewriting the laws of physics with a thought.
Okay.
But you might be sending low latency input, nudging the probability slightly, pushing towards a preferred outcome.
But only within limits. Right. The plausibility filter again.
Exactly. It always has to be plausible within the system's noise and constraints. You might be able to subtly influence quantum fluctuations to, say, find a parking spot.
Or manifest that extra cup of coffee, as the source cheekily suggests.
Right. That might be within the computational noise. But instantly manifesting $1 million or a sports car that's likely far too computationally expensive violates too many established data points. The plausibility filter says no.
So our minds are like very low-level programming tools nudging the system.
That's one way to think about it, yeah. Interacting with the probability distributions.
Okay, wow. So if the universe is this big dynamic computation, potentially with glitches and optimization issues,
then the biggest problems in cosmology might not be problems with physics itself.
They might be computational artifacts, errors, glitches in the matrix, essentially.
Which brings us to the big four issues that conventional physics is, as Count Zero puts it, QQing about.
Right. Dark energy, dark matter, the Hubble tension, and the big one, unifying general relativity and quantum mechanics.
QuQ's diagnosis for all of these is pretty straightforward.
Which is?
Physics isn't broken. Physicists are just looking at the output, the rendered result, instead of the source code. They're inventing new physical things like exotic particles to explain the glitches.
When maybe they should be looking at the operating system itself.
Precisely.
Okay, let's take them one by one. Dark energy. This mysterious force speeding up the universe's expansion. How does QuQ explain that in computational terms?
Simple. It's a cosmic RAM leak.
A RAM leak, like in my computer.
Kind of. In QuQ, the universe's volume is expanding because the amount of unresolved quantum information and information entropy is constantly growing.
So more information, more complexity.
Requires more space in the system.
Hmm.
This information bloat, this RAM leak, forces the system to allocate more resources, which manifests physically as expanding volume. The system has to grow to accommodate the increasing information load.
So the expansion isn't just happening, it's driven by information pressure.
Exactly. Mathematically, they model this using something called a modified Lagrangian approach. It's a way to describe system dynamics.
Wow.
The accumulating information entropy across the quantum mesh creates a negative pressure.
And that negative pressure is dark energy.
That's the claim. It's an emergent effect of information growth, not some mysterious physical fluid.
And this is where it gets kind of spooky because the source material claims QuQ actually predicts the density of dark energy.
And predicts it incredibly well.
How?
Well, the observed value is around 5 times 10 to the minus 10 joules per cubic meter. The QuQ equation derived purely from these information theoretic ideas.
Yeah.
It yields a prediction of about 4.82 times 10 to the minus 10 joules per cubic meter.
Wait, that's really close, like 2% accuracy.
Exactly, about 2% accuracy. And getting that value in standard cosmology requires enormous, frankly, unexplained fine-tuning. QuQ claims to derive it naturally from the system's informational dynamics.
Okay, that's startlingly specific. What about dark matter, then? The invisible stuff holding galaxies together gravitationally.
QuQ calls that the unloaded geometry buffer.
Unloaded geometry buffer. Sound like a graphics card issue.
Right. If dark energy is pressure from information entropy, dark matter is seen as a gravitational side effect, specifically a side effect of persistent quantum entanglement across vast distances.
Entanglement? How does entanglement create gravity?
Well, it's quantified by this term, gamma, the entanglement dilution factor. Think of gamma as describing how smeared out these quantum connections are across space.
So, the idea is that mass or energy exists, but it hasn't been fully rendered into our local, visible reality yet. The geometry is unloaded.
Pretty much. But even though it's not fully rendered locally, it's still entangled with the visible matter we do see. And those entanglement links, those data connections.
They still exert a gravitational influence.
That's the proposal. The gravitational effect is a byproduct of the information links, the entanglement. The links themselves are modeled as instantaneous, like direct memory addressing in a computer.
Direct memory addressing.
Right. But the actual mass energy geometry associated with those links hasn't fully resolved in our local frame. But its gravitational pull is still felt.
And does this model predict anything about dark matter density?
It does. The predicted value from the QuQ model comes out around 3.16 times 10 to the minus 10 joules per cubic meter.
And the observed value?
Observed is roughly 10 to the minus 10 joules per cubic meter. So it's not as precise as the dark energy prediction.
But it's in the right ballpark.
Exactly. It provides an order of magnitude match, which again is claimed to arise naturally from the entanglement structure, not by inventing new particles.
And the source also mentions other interpretations falling out of this computational view.
Yeah, briefly, like black holes being seen as memory overflow zones, places where information density becomes so extreme it exceeds the local processing capacity.
And quantum entanglement itself.
That's the direct memory addressing we mentioned. Instantaneous connections across the data structure. It all tries to tie together.
Compelling. Okay, third big problem, the Hubble tension. This disagreement about how fast the universe is expanding right now.
Right. Measurements of the nearby universe suggest a faster expansion rate, but 73 kilometers per second per megaparsec.
While measurements based on the early universe, like the cosmic microwave background, suggest a slower rate, around 67.
And they both seem right, experimentally. It's a real tension.
How does a laggy GPU explain this?
QuQ calls it a cosmic FPS issue. Fluctuations in the universe's frame rate, basically.
Frame rate. Seriously.
Metaphorically, yes. The explanation involved proposing that a fundamental scale in the system, the entanglement scale, LT, isn't constant. It oscillates over cosmic time.
LT. What's the entanglement scale?
It's roughly the minimum length scale over which quantum entanglement effects remain coherent or dominant in the system's computation.
Okay, so this fundamental scale, it wobbles. It gets bigger and smaller over time.
That's the idea. And if LT oscillates, the computational efficiency of the universe, its frame rate, would also vary.
How does that affect the expansion measurement?
Well, when LT is smaller, entanglement is more localized. The system might process expansion dynamics differently, making the apparent local expansion rate seem faster.
And when LT is larger?
Entanglement is more spread out, more diffuse. The processing might average things differently, making the apparent expansion rate seem slower, more like the early universe average.
So the Hubble constant, H0, isn't actually constant.
Not truly constant in this model. It's a dynamic variable that oscillates around some mean value over vast timescales.
Does this oscillation model actually match the numbers? The gap is about 6 kilometers MPC.
Remarkably, yes. By assuming a plausible amplitude for this cosmic oscillation of LT, the QuQ model predicts a difference, a base zero, between measurements made at different cosmic epochs.
And that difference is?
Around 5 kilometers of base E.
Wow, that's right, in line with the observed tension.
Exactly. So in the QuQ view, the Hubble tension isn't an error. It's observational evidence of the system's dynamic oscillating nature. Proof that the frame rate isn't steady.
This is, well, it's a lot to take in. QuQ isn't just a fun analogy about GPUs. It seems to be a genuinely rigorous framework.
It attempts to be, yes. It uses information theory to try and unify general relativity and quantum mechanics, which is the holy grail, right?
Absolutely. And it doesn't just talk philosophy, it generates actual equations, testable predictions.
And those predictions, particularly for dark energy and the Hubble tension, show really impressive agreement with observations, much better than you might expect from something that started partly as a cosmic troll.
Which makes Count Zero's prediction about how physicists might react feel uncomfortably plausible.
3 stages. Stage 1, laughter. Dismissing it as a joke, absurd.
Stage 2,
horror. When they actually run the numbers and realize, wait, these equations seem to work. Have we been looking at everything completely backward?
And stage 3?
Reverence. Acceptance, maybe, that the universe really is fundamentally computational, that information is the base layer.
So if this view holds any water, if the universe is computational, then we haven't just been observing reality.
We might have just stumbled upon the debug console.
Finding the underlying code.
Right. The core idea is that space-time, cosmic evolution, maybe even the fundamental forces, are all emergent properties governed by quantum information dynamics, by computational efficiency. Reality is this open system, constantly writing, rewriting, optimizing itself.
Which leaves us with a pretty profound final thought.
Yeah. The question stops being whether reality is running some kind of program.
And becomes, are you just passively watching the code execute? Or are you maybe, just maybe, ready to start debugging it?
Can we somehow learn to hack reality? That's the ultimate provocation here.